Problem 16.90. In this problem, an electrical heater with a total surface area of 0.25 meters squared and an emissivity of 0.75 is in a room where the air has a temperature of 20 Celsius and the walls are at 10 Celsius. When the heater consumes 5 watts of electrical power, its surface has a steady temperature of 120 Celsius. We need to determine the temperature of the heater of the surface when it consumes 700 watts. We need to solve the problem first by assuming that we neglect radiation, and the second part we're going to take radiation into effect, and based on our results we're going to talk about whether the assumption in part A is appropriate or not. Okay, start with the first part in which we assume that we neglect radiation. In that case, the amount of electrical power is going to be equal to the amount of heat lost by convection only. So if we have that the value that we had at the beginning is going to be equal to the amount of the heat transfer coefficient, the surface area, and the difference between the surface temperature and the air temperature. Notice that in this case, the information of the heat transfer coefficient is not given. That is why a value of electrical power and a surface tension is provided so that we could find the value of H to solve the problem. So the first thing that we're going to do is we're going to solve for H using the values. So we solve this information for H, and that is going to be equal to the electrical power, the surface area, Ts minus T infinity. Once again, notice for this values, we're going to use the 500 watts that were provided, the surface area, and the temperature that corresponds to that electrical power, which is 120 Celsius. Calculating this value, we get 20 watts m squared Celsius or Kelvin. Once again, remember that the unit for H could be either Celsius or Kelvin because the delta of Celsius and the delta of Kelvin is the same. Using this information of H, we're going to solve this equation for the surface temperature. So the surface temperature is simply going to be the value of the electrical power divided by the convection coefficient, surface area, plus the air temperature. So for this case, we're going to use the value of 700 watts. We're going to use the calculated value of H. The surface area. And the air temperature, which was given to be 20 Celsius. When we calculate this, we find that the surface tension, surface temperature, is equal to 160 Celsius. Once again, this part is by neglecting the amount of radiation. For part B, we're going to use both radiation and convection. Therefore, the amount of electrical power is going to be equal to the amount of convection plus the amount of heat rate loss by radiation. Okay, so if we rewrite the equation, we find that the amount of radiation is going to be epsilon surface area, Stefan-Boltzmann constant, surface temperature to the fourth, minus T surrounding to the fourth, and the amount of convection is going to be equal to H AS Ts minus T infinity. So notice once again that the amount of the heat transfer coefficient, it is not provided in this case, and that is what we need to do first. So we're going to solve this equation for H. So H is going to be equal to the amount of electrical power minus epsilon surface area sigma Ts to the 4 minus T surrounding to the fourth divided by the surface area Ts minus T infinity. Okay, so let's substitute the values for this. Notice that once again we're using the value of 500 watts. The value of epsilon is given to be 0.75. The surface area is given to be 0.25 meters square. The Stephens-Boltzmann constant is equal to 567 times 10 to the negative 8 watts m squared k to the fourth. For the radiation, we're going to use the temperatures in Kelvin. So let's review. So for the surface temperature, we have 120 Celsius. That is equivalent to 393 Kelvin. The surrounding temperature, it is equal to 10 Celsius. That corresponds to 283 Kelvin. So those are the values that we're going to use in here. 393 Kelvin to the fourth minus 283 Kelvin to the fourth. And we're gonna divide this by the surface area. It's 0.25 meters square. Now for the convection, you could do it either in Kelvin or in Celsius. There is no difference. Just to be consistent, we're gonna do it in Kelvin. So T infinity is given to be 20 Celsius, which is equal to 293 Kelvin. So we're going to do the surface temperature is 393 Kelvin minus 293 Kelvin. Okay, and after we plug it in, we put it in the calculator and we find that this is going to be equal to 12.58 watts m squared. Okay. Now once we have the value of H, then we need to find what is the value of the surface temperature. Okay, so we're gonna simply take and substitute the values in this original equation that we have over here. Okay, so we're going to have 700 watts, and that is going to be equal to 0.75 times 0.25 meters squared for the surface area. 567 times 10 to the negative 8 watts m squared Kelvin to the fourth. And this is where you start adding your unknowns. What we have is surface temperature to the fourth, and then we have 283 Kelvin to the fourth. We're gonna add the part of the convection in here, and that is going to be the value that we obtained previously for the value of H, which was 12.58 watts m squared K. The surface area 0.25 meters squared, and this is TS minus the ambient temperature, the fluid temperature, which was 293 Kelvin. It is very important that when you are solving for temperature and you have both convection and radiation, that your temperature is in Kelvin. You cannot have one in Kelvin and one in Celsius. You have to have both in Kelvin. Okay, so now we're gonna just simply multiply out what we have. So this is going to become 700. This multiplication of 0.75 times 0.25 squared times this Boltzmann's constant is going to give us 1.063 times 10 to the negative 8th, and this is TS to the fourth minus 283 Kelvin to the fourth. And then the second part over here, the multiplication of these two terms, is going to give us 3.145, and this is TS minus 293 Kelvin. Notice that this is a fourth degree polynomial, so we cannot solve it by hand. So you may choose to do it either by a graphic calculator, by MATLAB, or by Excel, whichever you're more comfortable with. I did it using a graphic calculator, so please make sure that you try it on your own. The answer that you should get is that the surface temperature is going to give you 425.9 Kelvin, or if we do it in Celsius, it's 152.9 Celsius. Okay, so notice one of the assignments was for us to compare the assumption of not using radiation or not. And notice that if we didn't use radiation, the surface temperature, it's 5 Celsius or 5 degrees lower than what we get using radiation, which indicates that having that assumption is not the best approach that we could have.